Good evening, everyone. Thank you for joining us for tonight's webinar entitled Exploring Our Oceans. I am James Kenley, the Executive Director for the Vail Symposium, and on behalf of our Board of Directors, welcome. The Vail Symposium has been offering affordable, thought-provoking programming to the Vail community and now beyond since 1971. We are a nonprofit organization, and ticket sales cover about 10% of our operating revenue. Donors at every level bring our mission to life in our community and make free programs like this one possible. I'd like to thank a few important organizations and individuals. Our presenting sponsors are discovervail.com, that's the town of Vail, the Frechette Family Foundation, and our event sponsors are Vail Resorts Epic Promise, the Vail Daily, and the Antlers at Vail. The Environmental Awareness Series is generously underwritten by Holly and Buck Elliott, and our virtual programs are sponsored by Alpine Bank. Our thanks to Rebecca Zweig of Business Smart Solutions for her partnership in designing this program and securing our incredible presenter. I will pause for your applause. Two items to be aware of before we get started. Please use the Q&A feature at the bottom of your screen to submit questions. You can type them in at any time, and we'll get to them towards the end of the program. We will run until about 7 p.m. Mountain tonight, and this program is being recorded and will be available for viewing in a few days. This is our final program of the winter season, and the summer will be announced in just a few weeks, but I'm happy to share a sneak preview with you now. We will kick off our summer season on June 1st with another webinar featuring the President of the Council on Foreign Relations for the last 20 years, Richard Haass. We'll be discussing the role of citizenship in American democracy. We'll have programs about Colorado cuisine, US-China relations, light therapy, Native American issues, clouds and sky watching, a backstage look at the Bravo Vail Classical Musical Festival, the debt ceiling, and what it's like to climb all of the 13,000-foot peaks in Colorado, and so much more. Recordings of our previous programs, the sign up for our mailing list, and of course, our donation page can be found at vailsymposium.org. Tonight, as many of us are planning spring break trips and summer vacations to beach destinations around the country and the world, I still have 2 feet of snow in my yard here in Vail, so the ocean sounds great right now. We thought that a program about our oceans would be appropriate. We are honored to welcome the president and director of the largest private nonprofit devoted to understanding the global ocean through world-class science and innovative technical development, Woods Hole Oceanographic Institution. A marine biologist and paleoclimatologist, Dr. Peter Menocal held esteemed faculty positions at Columbia University for over 30 years, and he founded Columbia's Center for Climate and Life, a climate solutions research accelerator. His many awards and distinctions would fill this hour that we have together, and I know that we're all eager to learn from his experience and discoveries. We are so grateful to Peter for spending his evening with us tonight, and I'll ask him now to imagine your applause as he takes the helm. Dr. Menocal.
James, thank you very much for the warm welcome. And Rebecca, thank you so much for reaching out. It's my pleasure to be speaking with you all tonight and to present something a little bit different from what you might be seeing there in the Mountain Time Zone, actually a discussion of the oceans. A bit about the wonder that inspires me, inspires our scientists to study the ocean, and then a bit about how the ocean is just fundamental to human sustainability, but in particular in solving the climate crisis. So with that, I will be happy to share my screen and see how successful this is. And here we go. I just want to get a thumbs up from James to make sure that is presenting correctly.
Looks great.
Okay, great. Thank you. So I'm very just pleased today to tell you a little bit about myself, literally for 10 seconds, and then to dive into the meat of the presentation. I've been a marine geologist and a climate scientist for 35 years. I spent 33 of those years in New York City at Columbia University, where I got my PhD in 1992. But my last post there was Dean of Science for the School of Arts and Sciences at Columbia. What brought me to the oceanographic was really the oceanographic itself. It's, as James mentioned, it's the largest oceanographic institution, independent institution in the world. And I invite those of you who might have the opportunity to come to Cape Cod on Woods Hole, Massachusetts, to please visit us. It's an amazing place to visit, and words really don't describe, but it's 1,000 people. And we have scientists, engineers, technicians, and seagoing professionals as well. So I'm here to talk about the ocean. The ocean is 71% of the surface of the Earth. And in fact, the Earth shouldn't be called Earth, it should be called ocean for that reason. We live on an ocean planet, and everything that we care about, our access or security of food, of water, shelter along the coastlines, and shelter internally in the interior of the continents, crop yields, climate stability, greenhouse gas concentrations, all of those things are regulated by the ocean. So those of you who are in the mountains and see yourselves being thousands of miles away from the ocean, rest assured that the ocean is directly linked to the snowfall you got this winter. The ocean is very much a hero for the planet. When we think about how climate evolves on this planet, it's very much linked to the changes in the surface condition of the ocean, and it makes sense. It's the majority of the surface area. But before I dig into some of the exploration and discovery that we do here at the Oceanographic, this is a view of, actually, my house is in this photo somewhere. This is a view of our dockside facilities, our sea facilities. We have 80 feet of water right off of our dock there. We have 2 global class ships, 4 ships, including our regional vessels. We have the only human-occupied submersible, Alvin, which is the only science vessel that can access 99% of the seafloor with its new pressure-rated depth to 6,500 meters. So it's a pretty big operation. We're, again, roughly 1,000 people, 200 PIs or principal investigators, and then, of course, technicians, engineers, and our marine operations professionals. And, you know, what makes the place distinct from my alma mater, my old institution at Columbia, is that we're independent. And by being independent, we're nimble. We're also entirely grant supported. So we have a $300 million a year budget, 85% of which comes from federal awards or federal grants. And every one of those grants is hard earned and has a success ratio for our scientists who compete for those of about 15%. So you can imagine the work that it takes to support the roughly 800 projects that we have going on at any one time. But really, being an oceanographer is about being at sea and conducting the work at sea. And it's a difficult place to work. This is a video of what it's like on a typical spring day, actually right about now, on the North Atlantic. This is off of one of our vessels. And that's a little bit what it's like when you're an oceanographer, as you get wet. And it's often pretty challenging environments to work in. But as we work on the surface of the ocean, we really also are engaging and see the life in the ocean. And this is a North Atlantic right whale. Those of you who know the story of the North Atlantic right whale is that this was the whale species that was most sought after. In fact, that's why it's called the right whale in the early whaling days here on Cape Cod and Nantucket. And these right whales were hunted nearly to extinction. But then there's this great whale repopulation success story that was associated with conservation efforts also at the Oceanographic. And those populations increased dramatically in the 70s and the 80s and even into the 90s. And more recently, in the last decade or so, they've begun declining again, and they're actually critically endangered right now. There's only about 300 individuals left in the world for the North Atlantic right whale, mainly due to entanglement in fishing gear and lobstering gear and ship strikes by the large super cargo ships that would strike one of these and they would never even know it. So we're doing a lot of conservation work to save these incredibly charismatic megafauna. As you go a little bit deeper in the ocean has an average depth of about 4,000 meters. And as you go down between, let's say, 200 and 1,000 meters below the surface, below the sunlit surface where we get all our fish from, there's a place called the ocean twilight zone. And this is a region of the ocean where the light goes to near extinction. And so were you to be able to see down here, your eyes could adjust, it would be a deep, deep indigo color in the water, or the light color would be this deep indigo. But you would think it might be depauperate in life, and it's actually the opposite. This is actually the location of the world's largest animal migration on the planet. And what it is life that's deep down in the ocean, around 1,000 meters, principally lanternfish, which are about the size of my finger, but they're in the trillions. And so it's much larger than any animal migration on the planet, on land. And it moves up and down every day with the sun. During the daytime, when the sun is shining, they dive down deep to avoid predation in the sunlit waters. And then at nighttime, they come up to the surface and they feed. And they follow this up and down in every ocean, everywhere. And so it's tracking the sun. This is a carbon pump. If you can imagine that these fish and these organisms are capturing carbon from the surface of the ocean and then taking it down a depth where they release it and they degrade their waste into the waters. And this is one of the reasons why the ocean is a tremendously large carbon sink. Indeed, it's the largest carbon reservoir, what we call exchangeable carbon reservoir in the world. There's 50 times more carbon in the full oceans than there is in the atmosphere. And it's really the sort of 800-pound gorilla of the climate system, of the carbon system. Now, getting down there is understandably pretty difficult. The pressures are tremendous. It's incredibly cold. It's on average about 4 to 2 degrees centigrade, almost at the point of freezing. So one of the ways that we explore this region is actually with sound. We have in this case, it's a mooring that we lower down. We anchor it to the seafloor, and it's tethered and it floats up to a depth of about 600 meters. And it's basically an inverted fish finder. So instead of pinging from a ship downward to look at fish below the ship, this actually has a very focused, sophisticated sound source in this yellow sphere that points upward. And basically it acts just like an ultrasound, as you might image a body part. This is how we image the ocean. And if you look at this, and these results are not even a year old, this is from the North Atlantic. These are from 4 different time periods here in August, September, and December. And the movement of fish and other organisms up to the sunlit portions during the nighttime. That's the red and the white lines going up, and then they go back down during the daytime. And so each one of these is about 2 weeks worth of continuous measurements. If you can imagine this going up and down in this location, this is this carbon pump. And this is one of the most detailed images that we have of this really hidden process in the ocean that have ever been recorded. Each one of these bars that goes across horizontally is about 2 weeks of measurements. And what this is showing is an ultrasound of the ocean. It's actually an image of the ocean life in this diel or daily vertical migration that's occurring in this location in the North Atlantic. And every up and down cycle is a carbon pump that's capturing carbon from the ocean, turning it into organic matter and being brought down below the surface. And this is one of the ways in which carbon gets pumped down to the deep sea. This is one of the most high resolution data sets that we've ever had to image this process. Mostly it's the cartoon that I showed earlier that people would show to demonstrate the ocean twilight zone and the vertical pump that happens there. This is one of the clearest images. Now, if you go down there with a submarine, or in this case, it's actually a robot we built specially to get these high resolution images. These are some of the alien creatures that you see down there about 1,000 meters deep in the water, almost a little over half a mile deep in the ocean. And you can see there's a lot of light. And this is actually how they communicate, both with each other and how they use light to evade predation. Now, if you want to go down to the deepest parts of the ocean to access the 99% of the seafloor that we can, this is our human-occupied vehicle, Alvin. And Alvin was just updated, really an entire rebuild of the vessel. It's about a $50 million vessel. And it consists of this titanium sphere. You can sort of see the portholes in the center of or in the front of the vehicle. And this vessel can dive down to 6,500 meters to access the deep sea with 3 passengers, 1 pilot and 2 scientists. And just to give you an idea of what we can see in the middle of the oceans, this is actually just an amazing footage, and I had to clip it down from a much longer footage, but fortunately it's fairly high resolution, high quality. This is from the North Atlantic Ridge. So in the middle of the North Atlantic, at the axis where Iceland is, for example, Iceland is an example of the Mid-Atlantic Ridge that's exploded up to the surface. But in the deep middle of the Atlantic is this ridge that's about 2,000 meters deep. And on that ridge, we discovered, in this case, several decades ago, these tube worms, entire ecosystems of tube worms and crabs and octopi and fish that live in the absence of photosynthesis. This is a whole new sphere of life that was discovered that extracts its livelihood not from the sun, but from the chemistry of the fluids that are coming out of these hydrothermal vents, as you can see here in this image. It's just every time we go down, we discover new species, new organisms. In fact, there was a species of fish that was just reported about 2 weeks ago. That was discovered. One of the ways that we can access the deep ocean in a sort of more comprehensive way is using autonomous vehicles, that is non-human occupied vehicles that are either tethered using a fiber optic cable, or that have the smarts built into them as they will, and the communications ability to go down on their own and conduct their missions autonomously, completely autonomously. This is a video of one of our vehicles called the Orpheus. And Orpheus was specifically built to be able to go down to the very deepest regions of the oceans. Alvin can only dive to about 6,500 meters. Orpheus can go anywhere. And Orpheus was built for 2 reasons. One is to autonomously explore the deep ocean. And we co-developed software that was used for the Mars Explorer lander to be able to map the seafloor in very much the same way we do on Mars, and to use that software to basically find our way on the seafloor and to map where we're going. And then we can use machine learning to say, there's something interesting. In this case, let's say a tube worm. And then we can communicate with a nearby vehicle and say, go back to this location and either re-image it, or in this case, sample it. This is, of course, an animation, but these are the vehicles actually that we have here at the Oceanographic, and everything that's in this cartoon is something that we do. It's pretty amazing that this technology exists, and we're actually developing it for what's called Ocean World. It's a NASA expedition to send vehicles, send spacecraft to other ocean worlds, such as some of the Mars, the moons of Jupiter. And so the idea is to actually develop these autonomous vehicles that can search for life on other planets. And these all can communicate with each other and form what's called intelligent sampling and intelligent navigation of the landscape. This is an image of my dear friend, Dawn Wright and Victor Vescovo, who just a few months ago dove to the deepest part of the ocean, the Challenger Deep. It's about 11 kilometers deep. And they went down in this sort of credit card looking vehicle and went to the bottom of the Challenger Deep. And I wish you were in front of me now, because I'd be asking you, what do you think they found there when they actually went to the very first dive site? This is what they found. The deepest part of the ocean, in pretty much the middle of the Pacific Ocean, they found a beer bottle. And this is one of the things I wanted to share with you, is that the oceans are changing rapidly, not only in terms of plastic pollution, and in this case, human waste and glass pollution, but they're also warming at an unprecedented rate. In fact, today it was announced that the oceans are warmer this week than they've ever been in recorded history. that is in recorded instrumental history. Not only are they warming, they're acidifying, they're changing, they're being overfished. There's a lot of things that are happening to the ocean. The oceans are in transition, they're in trouble. In my career, in my early part of my career, we thought the oceans were just too big to fail, and that's been replaced by a very sober understanding that we have to protect and preserve and understand the oceans at a pace with a degree of urgency that we've never had. And indeed, this is what brought me to the Woods Hole Oceanographic, because there are 3 institutions in the world maybe that can do this, and we're certainly one of them. What I would like to sort of pivot to today is understanding the ocean's role in the climate system. One of the takeaways from this presentation is that we do live on an ocean planet. The oceans are climate. Climate is the ocean. The changes that we're seeing in the ocean are, in fact, the foundation of the changes that we experience on land. 93% of the excess warming that's occurred because of human emissions that have accumulated in the atmosphere during the industrial or since the Industrial Revolution. 93% of that excess heating of global warming is in the ocean. And it's not just the surface of the ocean, it's being mixed down into the upper sort of 10% of the ocean or so. And that warming is what's contributing to these greater storms you're seeing in California, the greater snowfall that you're seeing in Colorado. And it's really a sign of how the oceans can really affect extreme weather. So for example, the flooding that's happening in Fort Lauderdale today, it was over a 1 in 1,000 year event that happened in Fort Lauderdale yesterday. And it really has no precedent. And part of the reason for this is that you get about 7% more moisture vapor in the atmosphere for every degree of warming in the ocean. And so that's what's supercharging these moisture systems, such as the Pineapple Express that comes into the Pacific, comes into the West Coast every year. But the thing that really got my attention actually last year was a statement in the Intergovernmental Panel on Climate Change report. It's called so-called AR6 report. And this was published in 2021, but was recapitulated in 2023, just a few weeks ago. And this statement really took my breath away. And the reason why is that it means that we have dallied for so long to reduce emissions. We've really not been successful in reducing emissions at the pace that's needed to avert truly catastrophic outcomes for us in our lives and mainly for our children. We've dallied so long, we've been ineffective in our actions that now all pathways that limit the future warming to 1.5 degrees centigrade or even 2 degrees centigrade now require carbon dioxide removal. And it's important to kind of get our heads around what carbon dioxide removal or CDR really means. Carbon dioxide removal is literally capturing carbon dioxide from the atmosphere, either by growing trees or by sucking it out of the atmosphere through direct capture or other means involving the ocean. But it's pulling carbon dioxide from the atmosphere to make it so that the atmosphere, the carbon in the atmosphere, that we reduce the climate risk, reduce the warming associated with that excess burden of carbon that's in the atmosphere. So you can think of CDR, carbon dioxide removal, as a way back time machine, kind of like Back to the Future. That is, if you can pull out carbon dioxide at scale, you can actually start reversing the climate risk. You can actually dial back to a time in the past when carbon dioxide levels were lower and we didn't have the extreme weather that we're experiencing today. But it's important to be really sober about what this means. Pulling carbon dioxide at scale is really hard. We measure emissions in gigatons, which is billions of tons per year. Just to get our head around it, 1 billion tons of carbon equivalent in freight trains of coal, for example. Just 1 gigaton is a train that would wrap 4 times around the equator. And we emit 40 of those units per year as a global society. So, trying to dial back that time machine to remove emissions, carbon from the atmosphere at the pace at which we're putting in the atmosphere is really a fool's errand. But once we're able to reduce emissions as we are doing through deployment of substitute of coal for natural gas, enhanced deployment of renewables. This CHIPS Act is fundamental. It's actually a fundamental leadership step by the United States to engage on the climate crisis. Once we can do that at scale, then you can start to remove carbon dioxide, to remove what's called legacy emissions. That is to get to remove carbon emissions at the scale where we can reduce climate risk. So some companies and some individuals, some corporations have really explored how to try to do this at scale. One is a direct air capture plant that was built by the Climeworks organization in Iceland. And it's basically a big vacuum cleaner for carbon dioxide. It uses nitrogen compounds that actually literally bond with carbon dioxide, capture it so it can be liquefied and stored and pumped in those pipes underground, either to reservoirs or to react with basalt rock to turn into limestone. So you can actually turn gas to limestone. It's a magnificent technology. It works in the lab, it works in nature. This plant is a wonderful thing. We should have lots of them. But in terms of the Wayback Time Machine, how much does this plant take up in carbon in terms of how much we emit every year? And this is the shocker, about 3 seconds of global emissions. Another idea that I'm sure many of you have heard about, certainly simple enough, is to grow a lot of trees. You can grow thousands, millions of trees. Great idea. One example is the effort to plant 100 million trees in the next several years. It's a wonderful idea put forward by Salesforce. 100 million trees, once they reach maturity, about a half an hour of global emissions. So it begins to give you an idea of the journey, the task that's before us. And this is really why I want to talk about the oceans again. The oceans, again, cover 70% of the planet, and the oceans are a natural carbon sink for the excess carbon that we're putting in the atmosphere. Basically, as the carbon builds up in the atmosphere, the CO2 builds up in the atmosphere, it acts like a piston to pushing the gas into the ocean. And this is the ocean's uptake of carbon through something called the solubility pump. Basically, if we were in a classroom right now and you had a glass of water in front of you, over the course of that lecture in that class, the water in your glass would become increasingly acidic because it's taking on additional carbon dioxide because the room is filling up with carbon dioxide because there are people in it who are breathing. And you can actually measure this. I used to do this in my classes at Columbia, and as you can do it, works every time. It's just basic physics and chemistry. And if you ask, what does the ocean do for us in this regard? The ocean takes up 3 months of global emissions every year, each and every year since the Industrial Revolution. The ocean has been an absolute climate hero for us. And it's because the oceans were equilibrated with an atmosphere where there were not people. Now there's lots of people and lots of carbon in the atmosphere, and it's unhappily taking up lots of carbon, and this is what's causing ocean acidification. But the ocean has really vast carbon storage potential. And the way to think about this is not just the skin of the ocean, which is where the carbon's going in the solubility pump, but really the full depth of the ocean, the full 4,000 meters of the ocean. And that's because the bottom of the ocean, the waters in the bottom of the ocean, are somewhere between 100 and 1,000 years old. And so the last time that those waters actually communicated with the atmosphere was that time ago. It was called a residence time. And so it means that the oceans collectively, the full ocean depths, represent this tremendous, vast carbon sink, if you will. Just to give you an idea of how vast it is, it's 50 times more carbon in the whole ocean than in the atmosphere. Or a kind of a shocking statistic is that you could take the entire excess carbon dioxide burden that's in the atmosphere now, the whole thing we're worried about for climate change, the full problem. And if you could get it all and mix it like a martini into the ocean, it would be about a 1% addition of carbon to this reservoir in the ocean. And the ocean has done this in the geologic past and many, many times. This is what the ocean does. It naturally takes up carbon, puts it away. So the question is, when we think about how carbon gets to the deep ocean, remember that rain of organic matter that goes to the bottom of the ocean. This is called the biologic pump. If you were to go down around 1,000 meters, it would look like a snowstorm. In fact, It's been called the greatest snowstorm on Earth when you're at that depth in the ocean. And it's that flow of carbon. So if there are ways to bring carbon down to the deep ocean, there's ways to durably store it for centuries to millennia to buy us time, which is what we need. Now, there was a National Academy study that was published about 1.5 years ago. The National Academies are the most respected independent scientific organization in the US, and I would argue the world. And there was a study that was led by this organization, led by some of the leading scientists around the world, to look at the ways in which the ocean can take up carbon dioxide in excess of what it takes up naturally. And there are 3 sort of leading ways that this can be done. The perhaps easiest one to understand is to somehow stimulate more productivity in the ocean so that organic rain rate to the deep ocean is increased. And that's this first idea of nutrient fertilization. I can tell you a bit about more of that if you're interested. A second one is perhaps a little bit harder to understand. It's called alkalinity enhancement. Basically, the oceans are not they're not neutral in the pH space. They're have an average pH of about 8.1. And that pH basically means that the ocean is a net sponge for carbon dioxide. So if there are ways to increase its alkalinity, it increases the natural ocean ability to take up carbon. And indeed, this is one way to offset ocean acidification. And a third way is just dead simple, is sinking seaweed. Literally, you grow and bale and sink seaweed so that you're capturing carbon in the surface ocean and it sinks to the bottom of the ocean where it degrades very, very slowly and carbon can be stored at scale. Now, I know what you're all thinking, what does the ocean care? How does the ocean care about this? Is this the right thing to do? Is it ethical? Is it advisable? And we don't know the answer to that yet. In fact, in none of these cases have they ever been deployed at scale. In none of these cases do we know the intended and unintended consequences or the efficiency of this. But in every one of these cases, they've been proven not only on the benchtop, not only in bays and smaller parts of the ocean, but in fairly large parts of the ocean. So for example, this nutrient fertilization approach was applied to a 100-kilometer in diameter gyre, if you will, in the ocean. You can literally write your name in the ocean. So the trick behind this, or the challenge behind this, is really comes down to an observations bottleneck. Some of you may know that we have robots in the ocean, not just the oceanographic, but some of the really larger oceanographics around the world. We all collaborate in a program called Argo, which are these autonomous robots that basically just pogo stick up and down in the ocean. They go down to a depth of 2 kilometers and they go back up to the surface. And when they go up and down, they measure temperature and salinity, in some cases oxygen, in some cases carbon as well. On the left is the Argo float that measures the primary, what we call state variables, temperature and salinity. On the right, though, is those Argo floats that measure the carbon system. And you'll see there's not many of them. We are basically flying blind on this problem. We have no eyes on the deep ocean. So all those things I was just telling you about, we really don't know how we would measure or report or verify the effectiveness of any of these measures to take up carbon from the atmosphere using ocean processes. And that's what the remainder of my presentation is about. We're proposing to build a 4D ocean internet of sensors. This is called MRV, or Measurement, Reporting, and Verification. So any carbon dioxide removal technology has to have a demonstrable MRV strategy or approach. We don't have that now in the ocean, but what I'm about to describe shows you that we're pretty darn close. This would be an always on, always connected, much in the way that we have for our satellites and our terrestrial measurements of wind and rain and temperature that we have in our backyards. We want to develop this for the oceans. It's an intelligent and adaptive sampling, so it's not just these dumb robots that they're actually not as smart as your toaster. They literally just float in the ocean like a neutral buoyant float. And when they come up to the surface, they make a phone call and they say, here are the measurements I made in this location, sends it out, and then goes back down again and does another measurement. It's a brilliant program, tremendously successful, but it's not really well adapted to this very specific problem of ocean CDR. So really the idea here is to turn on the lights for these deep ocean processes. So what might this look like? What I'm going to show you are some technologies that we've already established, not only at the Oceanographic, but at some other institutions as well. And basically it would consist of a central mooring site, which would be a big docking, sort of a garage, if you will, a vertical garage, where autonomous vehicles can navigate in. And first of all, you have to have power to this site. Well, this is something that we do already. We have windmills, solar power, and also wave power generated for moorings that are out in the middle of the ocean, away from any power source on land. So we have solved the power problem. Docking, if you have an autonomous vehicle that wants to come in and repower and download its data, you have to travel a long ways and find your way into a tube that's all just about as big a diameter as the vehicle itself. We do this already. Transferring data, we do this already. Repowering vehicles on the fly, we do this already. We also have communications whereby the information that's coming from this Sentinel site is sent up to the Starlink network through a 5G communication. It's difficult, but we're doing this, or we're working on this right now. And lastly, this concept of swarming and developing adaptive missions where vehicles can talk to each other and say, go over to this location, there was something interesting there, let's measure it again. So this is really this sort of new era of ocean observations. So we've given this a name at the Woods Hole Oceanographic. It's called the Ocean Vital Signs Network, and it's proposed to be twice the size of Texas, or 1 million square kilometers, full ocean depth, going from the surface all the way down to the bottom of the ocean in 4,000 or 5,000 meters of water. And the idea is to close the carbon budget in this, what's called a data cube. And it's this has never been done before. And what it lets us do is monitor and protect an ocean in transition, to study ocean health and how it's impacting fisheries, for example, but also to serve as a sandbox where we can try out some of these ocean CDR approaches and determine whether they are effective, whether they're safe, whether they're cost effective, and whether they're scalable. So this is a very simple animation we developed here at the Oceanographic, but on the right side would be the sort of standard biologic pump, the standard productivity in the ocean. And the right would be something that's enhanced, basically trying to quantify that green stuff, the flow of that green material of carbon, in this case, to the deep ocean. That's really the objective here, is to close that carbon budget. We can't do this now to within a factor of 4. I know this is what you're all thinking. So we've developed a 5-year roadmap for this. It's 5 years because we have to get this done. We have to begin this right now. This is really a need for an ocean in transition, and to really to protect the ocean as it is right now, but also to understand the ocean's potential ability to get us out of this pickle. We have written this up as a Gantt chart with initial framing, building an ocean internet, building the data model for this, developing full ocean climate models that capture the biologic and chemical processes. This is a little inside baseball, but it's roughly a $150 million venture. And a good question is, who's going to pay for this? How are we going to do this? And unsurprisingly, it involves partnerships. We have built an accelerator called the Ocean Climate Innovation Accelerator with a number of corporate partners in hard tech. The lead partner here was Analog Devices, a $8 billion company, actually quite a bit larger now, but their CEO and I met, and we had a great principal-to-principal conversation a couple of years ago. And he said, I want to do this. I want to get involved. And other companies are getting involved as well. And what's great is that not only do they contribute funding on the order of about $1 million a year for each of 3 years and these contract periods, but it's scalable because every company that joins will have that same deal. But the best part is that we get to bring in their talent, bring it with our talent, and work together toward these really important and difficult challenges. The other thing we did was, for those of you who know the engine at MIT, this is a venture capital fund that was developed at MIT. Moderna was one of their spinoffs, which was, of course, very successful. I met with the CEO of Engine, Katie Ray, a couple of years ago, introduced by one of our corporation members at the Oceanographic, Brian Halligan, who's the former CEO of HubSpot. And Brian was asking, why can't we do this? Why can't we just run these really large experiments? What's the block? And of course, funding our scientists to perform this risky, really important work is hard with federal funding. And we launched about a quarter ago, about 4 months ago now, Propeller, which is an ocean-based climate solutions venture capital fund, actually a hybrid fund. It's $110 million. And it's investing in technologies that we're developing here and elsewhere to solve the climate challenge. And the idea is to really provide this rapid funding to get scientists to work on these hard problems. Philanthropy, I could write a long list here of other companies that have been involved, or other foundations that have been involved. And the research collaboration, we have a joint program with MIT. It's the largest oceanographic graduate education program in the country. And it's been around for about 50 years, but we have a great research collaboration with them as well. And when we look at the federal funding horizon, it had previously been pretty low for carbon dioxide removal. And just in the last year or so, across agencies, and to be truthful on this, almost all of it's going for terrestrial-based solutions. But there's about $1 billion in federal funding from the National Science Foundation, NASA, NOAA, and the Department of Energy. So in terms of meeting the moment and trying to actually develop the climate solutions that we need and need so urgently, the key takeaway here, again, informed by how we responded to COVID, is we have to start now. We had to start yesterday, but we didn't. We have to start now. This is one of the reasons why I was happy to accept the invitation to speak to all of you, because I'm not just speaking to any audience here. I'm speaking to the Vail Symposium, and we have to make progress on this and have to do it quickly. We have to fund it at scale, a mix of philanthropic and other funding that's risk tolerant. We're building community, we're investing in people, and to my delight, the response of our scientists and engineers to really push the envelope of innovation is one of the most exciting parts of this venture. So I'm going to stop there, make sure we save some time for questions. And I just want to thank you all for your attention, and look forward to any questions you may have. Thank you.
Peter, that was wonderful. Thank you. I think it was well summed up by a comment that came in. This one did not have a question mark, but instead had exclamation marks. Wow, just wow, as a response to the first portion of that program. So
I love that.
Thank you. Thank you so much for the inspiration and hopefully some motivation here as well. Our audience, as always, has not disappointed us. We have a lot of questions, so we'll get right into it. This one, I think people have vacation on the mind, and the question is, what kind of an impact does the acidification of the ocean have on human activities like swimming?
So the actual acidification, those of you who remember any chemistry you may have had know that the pH scale is a logarithmic scale, which means that it increases by a factor of 10 for every change in unit in the pH scale. So the pH of the oceans have declined, have become more acidic by about 0.3 of a pH unit, which doesn't sound like much, but it's the difference between life and death if you're a clam or a coral reef. And that's because they build their shells out of calcium carbonate. And if you may not know your chemistry, you will remember if you put vinegar on calcium carbonate or limestone, it fizzes. And that's what's happening to our oysters and clams and calcium carbonate building organisms, which is actually a big chunk of the global ecosystem. So it doesn't affect people. It's a very modest change in acidification for swimming. But if you're an organism that makes its life basically taking nutrients and carbon out of the ocean to build a shell, it's life and death.
So this next question I think is really well aligned there. And whether you're talking about the alkalinity balance effort, the acidification, et cetera, but the question is around if we did manage to store the necessary carbon in the ocean to pursue 1.5, what do we think? What is the potential impact on ocean ecosystems? How would it feel that? I know you said it was a relatively low percentage, but maybe help us understand.
Yep. So, I mean, first of all, we haven't done anything like this at this scale. So it's never been done. So we don't really know the answer to that. But I can give you an example of an experiment that was done, published actually just about 4 months ago. This was a scientist and his students and postdocs that worked in the Australian coral reef region. And they did a deliberate increase in alkalinity in this sector of the ocean, a small part of the ocean. But they added a tracer to the alkalinity. So the alkalinity that they used was a calcium hydroxide solution that's very, very, very dilute. And it was released with a tracer so they could actually see the flow of this material in the water, how much it was mixing in. And they could actually see the carbon dioxide being sucked in from the atmosphere into the ocean. And it's basically reversing ocean acidification. And they could document that it worked. The reason why it's a relatively happy story is that they also measured the growth rate of coral reefs in that region. In other words, what was the impact on the coral reefs? And what they found is that the coral reefs actually grew better. And that's because they're not having to fight against the oceans becoming more acidic. It basically, if you want to grow really big, healthy clams, you grow them in more alkaline water. An example of this just in the natural world is the Mississippi River. The Mississippi River drains the interior of the United States, which is mostly limestone. And so the water that's coming in from the Mississippi and then being drained out of the Mississippi where it goes into the Gulf of Mexico, the Mississippi, that water is so alkaline relative to the ocean that it takes up tens of millions of tons of carbon dioxide just by that chemical reaction. It's amazing. The planet is amazing. But we have never done, a geoengineering of this at scale, and that's really what this is. And it's a very daunting prospect. And I just want to pause here, make sure that everyone understands that I am not an advocate for CDR on land or in the ocean. It is a place of last resort, and carbon dioxide removal is not a substitute for emissions reductions. Emissions reductions have to happen first before we could ever deploy this. The challenge or the problem is that we haven't reduced emissions enough, and we need to know how to take carbon out, because a 3-degree warmer world is a disaster. I mean, it's really, I could go on with a whole separate presentation on what that world looks like, but it's a scary one. And that's the path we're on right now.
There are a couple of questions here coupled in, and so I'll try to keep them aligned. But there's a couple of questions, people referencing the sargassum, the algae blooms that are happening, and how does that relate? How does that fit into the story?
Yeah, so it's called the Great Atlantic Sargassum Belt, and it basically goes from, well, it's in the equatorial Atlantic, so it goes from the Congo, if you will, right off of West Africa, along a line, if you will, in the equatorial Atlantic, follows the coast of Brazil and heads north, gets captured in the Gulf Stream, and it gets advected, it gets carried by the ocean currents, the Gulf Stream, such that it impacts, it washes up against most of the Caribbean islands, Mexico, and the United States. This year, actually right now, there is a freight train of sargassum weed that's actually longer than the East Coast continental margin. and it's the largest one that's ever been measured, and it's on its way now. And this expansion of sargassum weed is a new thing. It's only been in the last 10 years or so, and each year has been roughly a little bit more than the year before. And this year appears to be more than the last. What I can share with you is actually results that are not yet published. They were measured about 3 weeks ago, and we have what are called research ships of opportunity. They're called GO ships. And so if a scientific research vessel is going to a place where we want to get a sample of opportunity, let's say from the sargassum weed that's in the middle of the Atlantic Ocean, because right now it's hundreds of miles, 1,000 miles offshore of Brazil, and it's making its way on, it's slowly being carried in the currents. So we sent a ship out there to sample this weed. And we sampled the weed because you can measure the chemistry. You can do a geochemical fingerprint of the tissues of the seaweed, of the sargassum weed, to see what's different about it that's making it grow so much. And one of the discoveries we found was that, and this is work done by Dennis McGillicuddy here at the Woods Hole Oceanographic and his colleagues, what they discovered was that the seaweed has elevated nitrogen and phosphorus, particularly nitrogen. And guess where that's coming from? Agricultural runoff. But this is an example of what can happen when you have a runaway effect of human runoff on natural systems.
So this next question might help us understand maybe the human impact more specifically, but if we zoom kind of way out on a time horizon and we think back thousands of years, ice ages. I know you've got a background in kind of looking at history in the ocean floor. So I wonder how you can help us contextualize the macro rhythms of our climate, things like ice ages, warming times, cooling times. Help us understand kind of where we are now and how it fits relative to what we know.
Great, James. Yeah, that's actually my research area, so I can speak a little bit about that. As probably everyone in this call knows, the Earth has had past climate cycles that had nothing to do with people, and the climate has fluctuated naturally for millions upon millions upon billions of years. And this happens for some very long-term reasons, like the building of mountains and their erosion and dissolving to form salty seawater. And also for reasons that involve a wobble in the Earth's orbit. The Earth, our North Pole today is Polaris. If you look at that pointer stars, from the Big Dipper, count 5 measurements, and that gets you to the Polaris. That's our rotation axis today. But 10,000 years ago, or 1/2 of one of these wobble cycles called precession, our North Star was actually Vega, which is about 47 degrees in the opposite direction. And that's because of this wobble. And that wobble is what causes the ice ages. And so the Earth was about 6 degrees centigrade colder during the last ice age. Sea level was more than 300 feet lower than it is today during the last ice age. And there were ice ages upon ice ages upon ice ages, dozens upon dozens of ice ages. These natural glacial and interglacial cycles, or warm and cold cycles that were paced by this wobble in the Earth's orbit, actually did a really cool thing. And this is one of the reasons that we know that the ocean is part of the solution. During the last ice age, the carbon dioxide level in the atmosphere was about 1/3 lower than it is today. Well, lower than the pre-industrial value. It was 280 parts per million, before the Industrial Revolution. That's what we call the pre-industrial baseline. And it was 180 parts per million during the last ice age. And the biggest holy grail question in my career was solved about a decade ago. And that question was, where did that carbon go? And we looked in trees, we looked in soils, we looked in all the places you might think of, and we couldn't close that budget. And what we discovered was that it was hidden in the ocean, in the subsurface of the ocean. The ocean stored that carbon in the deeper Pacific and Indian Ocean and around the Southern Ocean. And it was stored there, higher carbon contents of the subsurface ocean. such that the deep oceans were higher nutrient, higher carbon, a little bit lower oxygen than they are today. And it's a natural cycle. So the ocean took up 100 parts per million. Now, if we were to do that today, and I'm not saying we can, this is a natural process that happened over thousands of years. So don't hold me to that, but 100 parts per million. If we did that right now today, that Wayback Time Machine example that I gave you gets us back to the year I was born.
Wow.
Yeah. So the ocean has this just tremendous natural capacity to take up carbon. And of course, we know that life thrived, during the glacial times and during the interglacial times. And, what's different about today, and really answering the question that was asked, what's different about today is that the rate of change is so different. The rate of climate change today is 2 orders of magnitude faster than anything that's happened naturally. And so if you need to know, like, how do we know that the warming is due to us today? It's because of the rapidity of the change. There's nothing like it that's happened in the many thousands of years that we can look in detail into the past. And we can also ascribe the changes to human emissions, not exclusively. Volcanoes matter, solar variability matters, those other things matter too. But right now, that's another question for your audience, is more than 100% of today's warming is due to greenhouse gas emissions. How can that be possible?
This question didn't come through the chat. This is an honest question for me, but you said in the ice age, the ocean was 300 feet lower. And I feel like the concern about rising oceans is over a much smaller delta. And maybe you can help us contextualize how we understand things like ice shelves and the ice caps and a rising ocean today in human terms versus a rising and falling ocean in Mother Earth terms, historic
Yeah,
terms.
no, I'm happy to answer that. So so sea level rise today, about half of the sea level rise is because of something called the steric effect, which is the warming of the ocean. Warmer water occupies more volume, just like a hot air balloon, but hot water balloon. So that is about half of the sea level rise increase, and the other half is melting of ice sheets. And Greenland and West Antarctica are losing mass like mad right now. And actually, the Antarctic is moving even faster. So at the time when we were born, sea level rise was about 1 millimeter per year, which is really small. But now it's over 3 millimeters a year. It's 3 times faster, the rate of sea level rise. Now, when the ice age sheets when the ice sheets melted about 15,000 years ago after the last ice age, the rate of sea level rise was about 10 times greater than what it is today. So that kind of sets a speed limit of what the system's capable of. And we are, accelerating toward that number. And so it's important to keep in mind that it may not feel like much, but sea level is going to go up a foot in about 20 years. So
and we're going to notice.
what I used to tell my students and their parents is, if you have a house on the water, go down to the high water mark, turn around, look back at your property, and anything that your eye intersects on a level is at risk.
Ooh. I expect that our audience is listening to that. I am mindful of the time, but there's one more question that has been asked several times that I feel is really important, and I'll add a little plug for the Vail Symposium before I ask it, which is that we are planning an ice shelf and climate change program for October of 2023. So for those of you waiting for the summer calendar to come out, keep your eyes out for that. It'll take that little soundbite from Dr. Menocal there and give us the context with some ice shelf experts. The question that's come up is around how can we, informed as we are now, how can we take action? How can we be supportive? How do we be an advocate for our oceans? Maybe help us feel like there's something we can do tomorrow to be better better citizens, better ocean advocates now that we're more aware?
Yeah, again, I turn to the lessons from COVID. What we did as a society was really miraculous. It was a record development of a vaccine in a very short amount of time, and it saved hundreds of millions of lives. That kind of mobilization didn't just happen. It happened because there was people globally felt a real mortal danger, and they responded to it. And part of the reason why I wanted to come speak to this audience is it's a sophisticated audience, and we have to look at the climate challenge with that same mortal grave danger, because it really is. That said, I really want to keep this on a positive and an encouraging note. And indeed, I'm an optimist. And I'm an optimist because I do believe we can understand. We can do a couple of things. One is we can do the emissions reductions we need to. It's not going to be 100%, but we can certainly turn it in that direction. That's already happening in most of the world's largest economies. But we're also making a lot of progress in these climate solutions, these ways in which we can actually reduce climate risk. And the reason this is possible is, frankly, philanthropy. It's philanthropy and partnering with industry, partnering with other institutions, and basically all of us coming together to solve the problem. The reason why philanthropy matters is because it's that early risk capital that lets you get people to work on it tomorrow. And so it's one of the early things that we can do to really make a difference. Federal funding is so important, but it's typically pretty siloed. It's risk averse, but it is at scale. But once you have a proof of concept, just like with the human genome, look what came out of that, right? And that's one of the reasons why we started Propeller. So again, I'm not a techno optimist, but I am certainly an optimist in the ingenuity of people when they put their minds to a solution.
I love that as our closing thought. And I know that we have an audience tuned in and online right now that will take that to heart as well. And on behalf of them and our organization and our community, we're so grateful, not just for your time and your expertise tonight, but for the work that the Oceanographic is doing. As a New Englander growing up, the Oceanographic was iconic and was legendary back then. And the work you're doing and the discoveries you're making are really inspiring. And we appreciate the work that's happening over there in Woods Hole. So thank you so much from all of us. And we wish you a really good summer. And I know there are more discoveries to come, so we will stay tuned in to the Woods Hole Oceanographic Institution. Ladies and gentlemen, I can't see you, but I know that you're as grateful as I am for Dr. Peter de Menocal. Thanks,
Great.
Peter.
Thank you, James. Thank you, Rebecca. Thank you, everyone.
Good night, everyone.
Good night.